Wave 7, longitudinal standing waves. Okay, if we get now when I do this experiment, I use a big measuring cylinder and a loudspeaker and a signal generator, and you turn it on, gradually increase the frequency of the sound, and at certain frequencies it's very, very loud because we get longitudinal standing waves. Here's another fantastic animation. You'll notice that the air molecules will be vibrating along the axis of the tube, up and down the tube. At the bottom of the tube there'll be a node, at the open end there'll be an antinode, and this is the fundamental. Okay, so for a tube closed at one end, this is the first harmonic. Now we don't get the second harmonic, we only get odd harmonics. We get the first, the third and the fifth, etc. because for a standing wave pattern, an open end must be an antinode and a closed end must be a node. Now, so for the first harmonic we have a node at the closed end and the open end is an antinode, but the second harmonic wouldn't be possible because that would be node. So we get the third harmonic. The fourth harmonic wouldn't be possible either, so we get the fifth harmonic, and you'll see there L is lambda over 4 or 3 lambda over 4 or 5 lambda over 4, etc. A harmonic is a multiple of the fundamental. A harmonic which is actually possible is called an overtone. Important that you appreciate these diagrams represent how the amplitude of the vibrations vary. The air molecules don't go sideways, they go along the axis of the tube, they oscillate up and down. These diagrams are just telling us how the amplitude varies. If we have a tube open at both ends, it sounds very different. Now why? Well, one thing is that the first harmonic is going to be different because now we have an antinode at both ends, so the length of the tube is half a wavelength. And the other big difference is that now all of the multiples of that will be possible. So we'll get the first harmonic, the second harmonic, the third harmonic, etc. So we'll get a different fundamental and a different bunch of harmonics. It will sound very different. Musical instruments, lots of them use air columns such as this flute, and sometimes, very often, they have stoppers like little buttons that you press or holes that you cover up, and what they do is they control the position of the nodes, and you can control the frequency that you get from the tube by controlling the position of the nodes. This is an important experiment you need to know. It's to find the speed of sound. There are different ways of doing it. This is how I do it. I change rather with my students, we change the length of the tube by adding water, and then for each length you find the fundamental frequency. Then from the maths on the right you should see that if we plot 4 times F against 1 over L, you get a straight line and the gradient tells you the speed of sound. Here's a question for you to have a go at, and I'll show you the answer in a couple of seconds.